going to talk about transformers today, electrical transformers. Somebody asked earlier, was the Optimus Prime variety? I said, alas, no. Not that kind of transformer.
This is Megatronics.
Yeah, it is. I mean, if we were going to talk about it, it would be now. So, let's talk about these for a few minutes. This is actually a relatively short lecture, which is nice. We'll probably get out of here on time for once. So transformers are two-port linear elements that consist of two tightly coupled coils of wire. What do I mean by two-port? Yeah, it has 4 terminals, so that means that, so we consider 2 terminals together to be a port, and so 4 terminals gives us 2-port element. And what do I mean by linear? Do you remember? I talked about it on Monday. The idea was that there is either an algebraic equation that's linear or a differential equation that's linear that describes the element's current voltage relationship. So the elemental equation, or equations in this case, are linear. So that's cool. Due to the coil's magnetic field interaction, time-varying current through one side induces a current in the other, and vice versa. So they're a little like an inductor, but instead of just storing that magnetic field or that energy in a magnetic field, it transfers it over to another side of the circuit. So one coil acts. You could think of it as being a transmitter, and the other one is a receiver, and vice versa. So, let the terminals on the primary or source side have label 1, and those on the secondary or load side have label 2. So, this is the circuit symbol that we use for a transformer. Very suggestive coils on here. And this is the 1 side. And this is the 2 side. So there's a voltage drop here, a voltage drop here. There's also, of course, a current flowing here and here. And these vertical bars in the center denote that there's a core associated with it, usually an iron core, and it just helps the transformer. Occasionally, we will not have this in there, in which case there might be an air core, in which case we'll leave off those vertical bars. But most of them have that. Okay. They're very efficient, so we often assume that there's no power loss. With this assumption, the power into the transformer must sum to 0, giving us 1 voltage current relationship. So the power going in port 1 plus the power going in port 2 must equal 0, right? And the instantaneous power, we know, is defined as being the voltage times the current. So this tells us that the product of voltage and current on one side is equal to negative product of the voltage and current on the other side. So that's one relationship between voltage and current. But with two ports, we need two elemental equations to fully describe this, because we need one elemental equation to describe the voltage-current relationship when we only had one voltage and one current. Now we have two voltages and two currents, so we need two equations. So power conservation gave us the one, this one. Now we're going to look to the physics of what goes on in there for the second equation. So this one can be found from the physics of the magnetic field interaction that we're not going to get into because we're primarily concerned with these as operating as input and output. We don't get into the design of transformers because we let electrical engineers do that. We focus on using these devices as sort of black boxes that have certain properties associated with them. So, this relationship is a pretty simple relationship. V1 over V2 is equal to 1 over N, where N is the ratio of the number of turns in the coil on the secondary side to the number of turns in the coil on the primary side, which is surprisingly simple. So it is mostly dependent on the number of turns in the coil. Now, clearly this is a bit of an approximation, right? This isn't going to be perfect. It's going to depend on how the coils are wound and how well it is constructed and all that. But we can say that this gets us a pretty good description of how these things work. And that's usually good enough for us. All right, so these two equations can be combined to form the following elemental equations. So if you use the first equation and then this equation together, we can solve for what the voltage on the load side or on the secondary side is equal to in terms of the voltage on the primary side, or the source side. So if we multiply V1 by N, we get V2. It's nice. The current on the other side is the negative 1 over N times I1. So the current's divided by N, and the voltage is multiplied by N. And that's the relationship. And so we have two elemental equations, and if we encounter a circuit, like say in the homework, with a transformer in it, we have now two elemental equations that describe it, and we can include those in our elemental equations and work out the algebra as usual. So this works for chapter 2 methods, where we have transient response included. This also works for chapter 3 methods with impedance as well. And we're going to do an example with impedance today. Notice that it doesn't involve a differential equation, which is super nice, right? We didn't have to worry about that. There's also we're not going to assume that it has any inherent impedance to it. It can, of course, transfer the effects of impedance through these two formulas, but it doesn't have any internal impedance, at least in our model. So, okay, so what are we going to use this transformer to do? So we can step down voltage if we make N less than 1. So notice that V2 is equal to N times V1, so if N is like 0.5, then V2 is half of whatever V1 is. This is better in some cases than the voltage divider because it doesn't dissipate much energy. since these are pretty efficient devices, you can step down the voltage without using a resistor, which is inherently going to dissipate energy. But there are some drawbacks to using a transformer, and here they are. The first is they're bulkier, so that's one. I didn't mention it, but they cost more than a resistor does. They are also a little more nonlinear because a resistor is one of the most linear elements you can get. Transformers are a little less so. So this is an approximation, of course, and you run into linearity issues occasionally. And then I think that there's one key aspect as well, and that is that a transformer doesn't work for DC signals. So it only works for AC signals. So you have to have an AC, a sinusoidal signal in order to use a transformer. Otherwise, do you guys remember what an inductor looks like to a DC signal? It just looks like a short, right? And there's no magnetic field produced, and there's no interaction between the coils. And this is actually used to our benefit at times because we can use that to describe, or not to describe, but rather to isolate two circuits from each other. So the DC component is completely missing from the interaction. So you can decouple the DC values of a circuit, which, for instance, when you want to isolate two circuits from each other in terms of the ground of each circuit, like so ground difference is going to be an offset, right? And you might want to interact with the circuit but not use its ground. That would be one way to do it. It's used. That principle is used in a lot of isolation circuits, but it's also, of course, used a lot. Transformers used a lot in other applications, not just to isolate circuits. So what other application are you familiar with transformers? Where did you hear about, besides Optimus Prime transformers, before this? What kind of transformer, when have you encountered a transformer? Power line. And it turns out that, so we assume that power is conserved in these, right? So if we step down or step up the voltage, we step down or step up the current simultaneously. So we're trading off between current and voltage here. So with power transmission, over long distances, the resistance of the wire used starts to become important. And if you have long distances of wire, you get more and more accumulation of this effective resistance and dissipation of power through that resistance. And it is advantageous to use high voltage when you transmit over long distances because there's less dissipation and low current. And then when you are at the place where you're delivering power to, like out on the power line outside your house, then you want to step down that voltage because they'll transmit it at like even up to like tens of thousands of volts. But when it gets to your house, that's not the voltage you want. You want it to be lower. So then transform it down to a higher current, lower voltage form of the signal. You lose a little bit, but you lose less than if you had transmitted it at the lower voltage and the higher current. So that's the idea with the transformers that you've seen. I told the other class was sort of like word of caution. So people always say things like voltage doesn't kill you, but current kills you, right? which is very misleading. It's voltage that gives us current usually. So when we have a voltage that's really large, the current that it can supply is often large too, especially if it's a power line. It's got a lot of power in it. So if you have a large potential difference and then you become part of the circuit, it's going to flow a lot of current. So that's the issue. Now, if the other issue with high voltage that you should be cautious with is that it can start to arc. So if you have a high potential difference, it can start to flow current through air if you get too close, even if it's not in contact, which is totally a bummer. You don't want that. That is not what you're looking for. I don't recommend high voltage running through you, or high voltage and then coming into contact with that circuit and then letting that current flow through you, or arcing too. I mean, the scary thing, like the linemen, I have a lot of respect for those people because that stuff, it can arc, and so they don't even have to have the lines in contact. If they're live, it could arc and you could become part of the circuit real fast. So yeah, scary stuff. I always am like, because we get a little bit, I think, I don't want to say we could become used to working with electricity in the lab, especially in this class. And you start to think, oh well, we work with all these components and electricity, and it's not that dangerous. Like, we're fine, right? But when you work with low power stuff, we can do that. We're probably gonna be fine if we get a little shock here and there. Not a big deal. But if you're working on, like, even your house has the potential it could be a pretty big deal. Even who understand how electronics work, I'm pretty cautious with even my house. I'll work on the electrical a little bit, but it does make me nervous. I much more prefer to be using a breadboard, something like that. Something that, like, if you do something stupid, it's just maybe your capacitor will explode. That's like the worst thing that could happen. A little fire starts on your thing. So I've been shocked by the 120 line before. It's not fun, and if you have like a heart condition or something, like you could definitely, your heart could stop. I mean, potentially you could die if you just get shocked, but clearly not a good move if you can avoid it. So just try to be careful. Whenever I talk about power lines, I try to caution people. It's like we were going to work with transformers in the lab a little bit, but the power you're transforming is not significant enough to cause this kind of stuff. So yeah, just a little word of warning. All right, so back to our discussion. We learned how to step down voltage if we have n less than 1. Something that's really nice is that we can step up voltage if we choose n greater than 1, which is something we can't do with a voltage divider. Voltage dividers can't become voltage multipliers. They're just dividers. So it's not amplification, however, because power is conserved, right? We simultaneously are stepping down the current. So you can trade off, right? So with a transformer, we can trade AC voltage and current. So let's do an example with a transformer. So given the circuit shown, what is the effective impedance? Oh, this is a typo. What is the effective impedance of ZL and the transformer combined? So we want to know the effect of this load impedance on this side of the transformer where it's connected to this source circuit. Now we're we're using these generic elements with just some impedance, right? Could be inductors or capacitors or resistors or whatever. So ZS for the source impedance and ZL for the load impedance. And it seems like a lot of times just getting started is the hard part with these problems, right? We've got to come up with a strategy. So when I wrote this problem, I also needed to solve it too. So I sat down and I thought, okay, I want to describe the impedance of essentially this port, right? The one port. So I want to describe Z1. So we want Z1. And we want to write it in terms of ZL, right? In terms of ZL. So it's good to sort of clearly understand what you're looking for. And then overall, we got to choose a strategy. And I think that, there are a lot of ways you could go about doing this. One way you could do it is you could go through a whole circuit analysis and solve for what VL is and see what its relationship to the current through it is. So you can just write all the equations down and then try to solve the whole thing, and then you know everything in the circuit, and then you would have an effective impedance there, which is a fine way of doing it. But we actually can do something less strenuous, and so it's good to think through how to do that. So if we're looking for Z1, we know that from the definition of Z1, it's just Z1. So from the definition of impedance, we know that Z1 is what?
V1 divided by I1.
Yeah, so it's just V over I, right? V1 over I1. So we know that, and we can use, we're trying to get over here and describe in terms of ZL, right? We can use the elemental equations of the transformer to convert V1 and I1 over to V2 and I2. And then we can relate V2 and I2 to VL and IL using essentially KCL, KVL. And then we are going to have an expression in terms of VL and IL, which, using the definition of the impedance of ZL, we can write in terms of ZL. So that's generally, like, on a high level what we're going to do. We're just going to bring these equations in as we need. So the first step is to use the transformer elemental equations. So the transformer elemental equations are listed on this page over here, the blue box. And they tell us how V2 and V1 and I2 and I1 are related. So we can rewrite these in terms of V1 and I1, right? So that one says V1 equals V2 over N, And this one says that I1 is equal to negative n times I2. So you can go either direction, right? From 1 to 2 or 2 to 1. So using those and just substituting them in for V1 and I1, we get that Z1 is equal to, our V1 was just equal to V2 over N, right? And our I1 was equal to what?
Negative n times I2.
Yeah. Great. So if we bring the factor negative 1 over n squared out front, we have negative 1 over n squared times v2 over I2. Great. So we've jumped through the transformer now. We picked up a factor of negative 1 over n squared. But now we're in the same loop as the load, right? And I put the sign on here, so we have to stick with it, that the current and the current flows in this direction, and the voltage drops in this direction for the load. So I did it so that the current IL going into this node is equal to the current I2 leaving the node, right? So this just said, so KCL would just say that I2 is just equal to IL, right? But if you did KVL around this loop, you would say V2 plus VL equals 0. Or V2 equals negative VL, right? I mean, it's really simple KVL. Sometimes the simplest ones are the ones that trip us up, right? So, say using KCL and KVL for the secondary loop. We see that we can insert for V2 and I2 these two expressions, right? And the only thing that really changes is I2 becomes IL, V2 becomes negative VL, so we just pick up a negative sign as we do that. So our Z1 is equal to, I'll just cancel it with this negative sign, so we have 1 over n squared times VL over IL. Okay, what's the last step?
VL over IL is 0.
Mm-hmm. So, from the definition of impedance, we say ZL equals VL over IL, and we can then finally write Z1 equals 1 over n squared ZL. So if we wanted to, we could draw ourselves a nice new circuit with our source impedance still there, ZS. And now instead of being connected to the transformer, it would be connected to this impedance Z1. right? Now that's you know, I mean, it sort of seems like a one-off analysis, but in fact, this is generalizable. So, anytime you have an impedance on one side of a transformer, it affects, or it is, you can say, felt by the circuit on the other side of the transformer through this factor of 1 over n squared. So this 1 over n squared is how the impedance is transformed to the transformer. Yeah. Useful stuff. So it's generally useful. Jeez. Okay. Any questions on that issue or on that problem and just transformers in general? Yeah.
Where'd you get the negative VL from?
Yeah. So if we were to do KVL around this loop, we would say that, so say we went this way, it would be V2 plus VL equals 0. Which gives us that, right? That V2 equals negative VL. The reason why the currents came out the same sign is that they were in the same direction around the loop. And it's, yeah, if we would have said, so would it have come out the same if we had chosen IL to go this way? Yes, because then I2 would be equal to negative IL and V2 would be equal to VL. So you get the negative sign no matter which way you slice it. So you always get this relationship, which is really, it's a useful one. And I think that you can sort of file this in the same place that you file, like, using voltage divider and current divider rules. It's a shortcut to finding the impedance on the other side of the transformer, which is really useful sometimes. But just as with the voltage divider and current divider, you can always go back to writing your elemental equations down, writing down KCL, writing down KVL, and solving for things, right? You can always do that. And so I sometimes feel like I shouldn't share some of these things with you guys because I feel like it muddies the water a little bit. They're meant to just be sort of shortcuts to finding what you want from a circuit, which I think they're really useful. But when you get confused, and if you're like me, you're often confused, you going back to the fundamentals of writing down the elemental equations and the KCL, KVL, and solving the, in case of impedances, algebraic system, that's like, we can always go back to that. And that should be the gold standard. You might not be able to remember that when you, they call this reflecting an impedance through a transformer, that when you reflect an impedance through a transformer, it picks up a factor of 1 over n squared. That's not something that I would remember off the top of my head. Well, actually, this one I do. But a lot of equations like this, I don't remember off the top of my head. And that's okay. And if you're ever like, I don't remember when that formula applies, that's often for me what'll happen is I'll remember the formula or the form of it, but I don't remember the special, if there's any sort of special case that's involved. So going back to the fundamentals is useful. Okay, you have one on your homework, and I think that you're going to be fine on it. It's this week's homework. I think it's not going to be too bad. And I apologize for those of you who went to the study session last night. I forgot to send Stefan the solution to the homework this week, so he was flying blind. So that was my bad. I shouldn't have failed that task. So, are there any other questions? I'm happy to entertain them. I've got 7 minutes. You have me for 7 minutes. Okay. Then I withdraw my offer. I wasn't gonna even help you anyways. So.